Hey everybody, it's Ripley. Welcome back. We're in 4.5. In L'Hospital's rule, it's actually not pronounced La Hospital. If you do, I'll look at you strangely. It's L'Hôpital, clearly by some German guy, I'm kidding, named Bob. No, it's a guy by the name of L'Hôpital who came up with an incredibly useful rule. All right, and what it all stems from is something called indeterminate forms. Nant forms of limits. All right, let me give you an example. Let me give you a few examples of indeterminate forms. First and foremost, as far as L'Hopital's rule is concerned, we use the rule when we have the form infinity over infinity or 0 over 0. Now, for example, remember this guy? The limit as x approaches 0 of sine of x over x. The proof of this, in absence of L'Hopital's rule, is extremely difficult to do. It's a pain in the butt. But you have to do it geometrically. It just takes forever, and you got to do all sorts of mathematical hand-waving. With L'Hopital's rule, it is so simple. All right, well, I'll show you it here in just a sec. I'll show you quite a few of these. All right. However, there are other forms of L'Hopital's rules. Now, this is all that L'Hopital works with, okay? However, let's talk about a couple of others. There's one, 0 to the 0. Now, look at 0 to the 0. On the face of it, you may say, well, if I have a limit and it ends up being 0 to the 0, like if I take the limit as x goes to 0 of x to the sine x, well, this gives me 0. When I plug it in, I end up with 0 to the 0. The problem is, who wins? Remember, algebraically speaking, theoretically, if I take 0 and I raise it to any non-zero number, this is always going to be 0. However, if I take a and I raise it to the 0, algebraically, it's supposed to be 1. So who wins this tug of war, this strange tug of war? Excuse me. Another example is infinity to the 0. Same sort of argument. I mean, infinity is infinity, right? However, who wins? So if I take the limit as x goes to 0 from the positive side of the natural log of x, and then if I raise this whole thing to the x, well, don't I know this is technically negative infinity, but it's really, it can be argued that it works the same way, to the 0. Well, again, infinity blows up. It gets there real quick. However, think of it like a race. Does the exponent raised to the 0 go to town more quickly, as it were? Okay, so that's another example of an indeterminate form. And then last but not least is one that you'll see, excuse me, like this. So an example of this would be like the limit as x goes to, well, what's a good one? How about 0 of cosine of x to the 1 over x. That's a good one, right? Because we know at 0, cosine of 0 goes to 1, and at 0, we should probably do this from the positive side, just to keep it honest, right? That it goes, so I end up with 1 to the infinity. Well, who wins? Do I get to 1 faster? Because 1 raised to any number is always 1. However, remember, we're taking a limit, so we're sneaking up on 0 so here's 0. I'm sneaking up on 0 from the right-hand side. So who wins this battle? Well, believe it or not, all of these indeterminate forms right here, which are what we call non-L'Hopital indeterminate forms, they're algebraically manipulatable most often, not always, but most often, to look like these guys. So let's start with these guys first, and let me give you the rule. It's so simple. All right, it's this. If the limit as x goes to a of f of x divided by g of x equals, all right, now equals is I'm going to leave kind of a question mark here because it doesn't really equal, right? But look, you know what? Instead of a question mark, let's use an implied arrow. If after plugging it in, I get the form either 0 over 0 or infinity over infinity. Now this could be plus or minus and plus or minus, right? So we're not afraid of that. Then this implies that the limit as x approaches a of f of x divided by g of x equals the limit as x approaches a of f prime of x divided by g prime of x. Yeah, that's pretty cool if you think about it. It's so simple. And the proof of it is unbelievably elegant. Check it out. Really think about it. I'm going to prove it for the 0 over 0 case. So the proof for 0 over 0, it's real simple. If I take the limit, since they're equal to one another, I'm going to start on the right-hand side because it's actually easier to prove. I'm going to take the limit as x approaches a of f primed of x, f primed of x, wow, my stylus is acting up today, g primed of x, right? And we know that what this guy turns into is, now think about here, since we're talking about a limit as x approaches a, I can actually, excuse me, I can write this thing up as g, I got g prime, right? By the plug it in property, excuse me, I can rewrite this thing as f primed of a over g primed of a. Now, notice all that I'm doing here is I'm starting on the right-hand side of L'Hopital's rule, and I'm just cruising, okay? Now, what does this equal? Well, we know this. This is the limit as x approaches a of f of x minus f of a over x minus a over the limit as x approaches a, it's an x, of g of x. Remember our definition of a derivative. I know some of you are trying to forget it. Please don't. Over x minus a, right? Gone. True? So this ends up being the limit as x approaches a of the limit of the quotient is the quotient of the limits, or the quotient of the limits is the limit of the quotients of f of x minus f of a over g of x minus g of a. But remember, f of a and g of a were 0. The way that we got here in the first place was f of a equals 0 and g of a equals 0, right? So these guys actually go away. This ends up being the limit as x approaches a of f of x over g of x. And because it's equal, even though it appears as though I proved it backwards, it's equal. I can start on the other side. Isn't that clever? The limit at infinity is a little bit more complicated, and it takes a little more time than we're willing to spend here, but that's okay. All right, you ready? You're going to love this. Watch. Remember how when we first started playing with this limit right here, let's take the limit as x goes to 0 of sine of x over x. Now the first thing we're going to do is plug it in. Oh no, Ripley, whatever shall we do? We get 0 over 0. There's no algebraic way to simplify this. Remember, your first tool that you're always going to pull out of the toolbox is algebraic simplification. So we pulled out our calculators and we used tables and we did all kinds of crazy things. However, what we're going to do is we're going to go equals by L'Hopital's. That's this little notation right here. You see this guy right here? Right here, this little h that I just put here over an equals sign. That implies that we used L'Hopital's. So that just tells you, that tells me as a grader, it tells all of your graders, okay, this kid just did L'Hopital's. Well, the derivative of sine is cosine. The derivative of x is 1, right? The limit of a quotient is the quotient of the limit. Limit as x approaches 0 of cos x is 1. The limit as x approaches anything of 1 is 1. And you're done. Isn't that awesome? So simple. So simple. Piece of cake. Let me give you another example. How about this guy? How about the limit as x goes to infinity of x squared over e to the x? Let's do this guy. All right, clearly, when I plug it in, I get infinity over infinity. All right? So, by L'Hopital's. Now, before we do this, notice this is the notation that I use, so an equal sign with an h over it. Let's think about this. They're both heading for infinity. The question is, who gets there first? Or do they get there at the same time? In other words, does e to the x get to infinity faster than x squared gets to infinity? Well, I think our intuition tells us exponential functions grow really, really fast. But, excuse me, let's check it out. The limit as x approaches infinity of, 2x over the derivative of e to the x is e to the x. Ah, crud. I get infinity over infinity again. Well, shucks. I'm not afraid. I'm just going to keep using L'Hopital's. That's the best part about L'Hopital's. Anytime that you get an indeterminate form, you can keep using it. The problem is if you start losing indeterminate forms, Not so much with the goodness, okay? So let's see, what do I want to do here? This is going to equal the limit. I start telling stupid jokes, and I end up losing track. This ends up being 2 over e to the x. And look at what happens. This is 2 over infinity. Last I checked, that's 0. Now, look at what just happened. A number of things. We got so much information. We ended up getting, we figured out that e to the x grows faster than x squared. So out at infinity, we know that e to the x wins the war. We also know that if I have f of x equals x squared over e to the x, remember, if I take a limit at infinity and it equals a number, guess what? Y equals 0 is a horizontal asymptote. I have this wonderful new tool to be able to figure out how to find horizontal asymptotes. Isn't that cool? That's really fun.